this evening. This is great. So let me give you a general sense of what my plan is. Um, I want to make sure as many people as there can be see the new generics syntax, or at least what's being proposed in the draft right now. So many of us are busy working and got busy lives. We don't really have the opportunity to just sit down and read the draft or even play with it. And this is such an important new feature to the language that we need as many people as possible to have some sort of opinion or say in it. So over the next hour, it is 45 minutes past the hour right now. So I'm only going to use an hour here to show you as much of the new draft syntax as I can. And I will be able to get through, I think, at least 85, 90% of it, okay? After that, I will then take questions. It's just too hard to take questions during the talk. But please feel free to chat amongst yourselves in the Zoom chat and talk it up there, like no holds barred, okay? And then because we're such a small group, I would love to give everybody like 2 minutes to voice an opinion if you want to. I like doing that when we have such a small group, so I can hear everybody's feedback. And yeah, and we'll do this over an hour and a half or a little more if we all have time. All right, so I'm gonna go ahead and share my screen. And the first thing I'm gonna do here actually is put into the chat window 3 links. Okay, there. Somebody's mic is on as well. We gotta mute that. I'm not sure who that is. So these are the 3 links for the talk today. The first link is to this GitHub repo that I'm showing right now. The second link is a link to the draft document, and the third link is a Google survey that will give you an opportunity to give feedback directly to the team. We'll talk more about that at the end. But here's the Go training repo. It's that first link that I gave you. You can see here that I currently have 11 examples. We're only going to have time to go through the first 5. That's it. So the rest of these are going to be for you to look at on your own. They're well documented. If you go into the README, you'll see a link right over here in that first sentence. That's going to bring you to the draft design document. It is a draft design. We'll talk more about that in a second. But if you do want to read that, there it is. Also, there is a playground for experimenting and trying out the new syntax. I'm going to spend an hour going through this. I won't be using the playground. I'll be running everything on my local machine. I have instructions for doing that as well. I'm not going to read this, but this is the very high level overview of what the current draft is looking at in terms of a first release for generics. And I'll be sharing most of this with you over the next hour. I'm not going to read it. I took it from the draft document. And then anyone who has questions about what is not currently slated for the first release, there it is. These are the omissions. It doesn't mean that these things may not make it in for first release. They're just not being worked on, at least right now. I don't really expect them to be in a first release either, but anything can change at any time. And then outside of some extra reading, these are the instructions for being able to run this Go tooling locally on your machine. It's essentially downloading the source code for Go and building it. And that's exactly what I'm going to be doing today. So you see here that I've typed Go version. You can see that I actually built it this morning, but that source code is back from August 1st is the last time they've made any changes to that branch. So you see here, it doesn't say 114. We're going to be running the latest Go tooling. And on that note, right before we get into some code, I want to stress to you that this has not been implemented yet. This is critically important here. Generics has not been implemented. What we have right now is a tool called Go2Go, which is a transpiler, so we can play with syntax. So we're essentially has a tool that will take the syntax that I'm going to show you underneath the covers, convert it to working Go code, and then build and run it. So there is absolutely no implementation of generics at all. We can talk a little bit more about that at the end as well. Okay, I think with all that being said, and with the time constraints we have, it is time to jump in. Now, as I show you code here, one of the things that I would love for you to do, also chatting it up and expressing your thoughts in the chat with your local group here, is look at the syntax, ask yourself if this still looks and feels like Go. Ask yourself, do you feel like the choices right now that we're at are good? I'm going to express my opinions as well as we go on, especially where I think the syntax is starting to potentially be in a gray area. But you know, your thoughts and opinions are important here, and this is kind of your opportunity to kind of express that. Okay, let's get right into it. You'll notice that these files have a go-to extension for the tooling. We're going to start with a basic generic function, but before we do, I want to walk through a progression so we can get a good sense of also, by the time I'm done, what problems we think that this draft of generics, this first version of generics, will help solve. And you know, well, let's just say help solve at this point. Okay, so let's start here. Let's say I wanted to write a print function that could take, in this case, a slice of integers, like you see on line 13, iterate in a linear traversal over that slice of integers, printing out each individual integer one at a time. So if you look at the print numbers function here on line 13, you see that I have 5 lines of code to do that. I've got a header, I've got a carriage return line feed at the bottom, we've got our traditional for range for that linear traversal, and we're using the print function to print each integer out with a space. You know, here it is. It's 5 lines of code to do what I want to do. And I will make the argument that I think most Go developers at almost any level, even if you've only been working in Go for a couple of weeks, if you have a programming background, right, you can read and comprehend this code. And it's one of the beautiful things we love about Go is that there's a lot of code just like this where you can come into the language new, be able to read it, comprehend it, and maintain it. And I think this code showcases that really well. Now, if I decided that I wanted to do the same thing, but with a slice of strings, a collection of strings, well, since the type has to change for the collection type, right? Here's going to go from int to string. I have to basically copy and paste some code. I'll change the function name out. I'll change the variables names to make them make more sense. But look, it's the same 5 lines of code, isn't it? Really, right? A header, carriage return, for range linear traversal, and we print it. It's the same 5 lines of code, just working with a different type of data. And if I wanted to do this one more time with floating point numbers, well, I got to write another function. So on one hand, because each function is so tailored and specific to the type that we're going to be working with, the code is more readable and consumable, right? There's nothing fancy going on here, but at the same time, it's tedious because for every type of data I want to print, I've got to basically write another function. So from this point here, we could ask ourselves, is there a way to consolidate all of these types of functions, like for my slice of int and string in this case, into a single function? Is there a way to consolidate this? Maybe it will help us maintain the code base better. And the answer is yes, we can consolidate. We can do that with 2 mechanics in Go. We can use the empty interface as a way to accept a slice of any type. In fact, we can accept data of any type using the empty interface. And then we can use type assertions And on the switch statement, we have a generic way of doing a type assertion. And then we can use each case statement kind of like an if to validate, did we pass in a slice of int? Did we pass in a slice of string? And then we can perform that, in this case, that linear traversal using the same exact for range and mechanics that we all, at least I agree, is easier to read and comprehend by most Go developers. But this isn't a generic function, right? It's more of a consolidation of the other functions into one, because if I pass a slice of float 64 through here, we ain't going to get any output. I don't have a case for that. So I have been able to maybe reduce some of the maintainability by consolidating this into a single function. But if I want to print out more types, I have more coding to do. So then the question is there a way to write this print function in a generic way today in 1.14? And the answer is yes, there is. I mean, we can leverage the empty interface one more time to accept a slice of any type. And thanks to a package in the standard library called reflect, we can at runtime reflect over the data and perform operations. So as you see here, we always start out with that value of call. We get this reflect value back. We can validate that we have a slice to begin with. Now, this does change the semantics a little bit, because if it's not a slice, we have to return something, and the other functions don't have this semantic because we're guaranteed what the type of the slice is here, or at least the data that we're passing in, we're guaranteed that was a slice of int or string. You are not here. So this changes the semantics a little bit, but given the fact that we do get a slice, we don't care what type of slice it is. We can't use our for range loop. That's kind of a bummer, but we can increment I and index into each element like you see here using that method index. And then we use the interface to get back to the data, and then we can print that right there. And so with the reflect package, I'm able to write a generic version of print that can print not just that slice of int and string, but that slice of float. Now let's be real though. The other functions that we wrote were 5 lines of code. This one is 8 lines of code. We've had to write more code, and I can't make the same argument that Go developers at all levels can come in and quickly read and comprehend this code. I mean, I even had to look up the documentation in the reflect package to write this code. Now, I am a big fan of reflection. I'm not here to say anything negative about reflection. I think reflection is a amazing, powerful tool we have in Go. In fact, the print function that I'm using here is leveraging reflection to be able to generically print values of any type, right? I'm leveraging that. So I'm a big fan of the reflect package. I am. But again, what's happening here is that if I want to make this code generic, I have to walk away from writing the code that I would have written if it was an int or a string. And now I'm working with an API. And so the code isn't as intuitive, it's more complex, but it does, in this case, serve that purpose of generics. So the question then is there value in being able to write code like this, okay, where we know that the majority of developers here can read and comprehend this, but not have this code written like this tied to a single concrete type? Is there value in being able to write code as if we're working with a concrete type, though we won't know what that concrete type is until we hit that build button? And I think the answer is yes. I think there is value in being able to write a generic function of print without the need or complexity of the reflect package in this particular case. I mean, if I was still writing code that was going to do data validation or marshaling and unmarshaling, I'd probably still use the reflect package. There are big wins there. So let's take a look at a generic version of our print function based on the current syntax being proposed by the draft document. And we see this here on line 75. And what I want you to focus on for a second is the fact that I am using the same 5 lines of code that I used originally when we were working with that slice of int and string, the same 5 lines of code that I made the suggestion that most Go developers at any level can read and comprehend. That's beautiful. Now, I want to break down the new syntax for you first so we can understand what's happening here. I'm going to do that by kind of removing it, and then we'll bring it back in and we'll talk about it. Now, ideally, what I'm trying to do, or the code that I want to write, is basically this, right? I want to tell the compiler that I would like to accept a slice of some type T. The whole point here is that T is not defined by me, right? That T is a generic type to be determined at compile time. This is what I want to tell the compiler. The problem is that this idea of T isn't just enough, right? Because this code is no different than that int or the string code that we saw. The compiler, with what I've done here, is assuming that before I hit the build button, that somebody somewhere in some source code file is going to define a type T, whether that's using the keyword struct or an underlying type. The compiler assumes with this syntax that T will be defined in some source code file before we hit build by some developer. And the reality here is that T is not going to be defined. We don't want to define something new called T. We want T to be a substitute for an existing type to be determined at compile time. And this is why we need some new syntax, because this in and of itself doesn't work. So the current draft says if you want to tell the compiler that T is going to be a type identifier of some type to be determined at compile time, then we're going to use these square brackets. We're going to use the keyword type, and then we're going to list out those type identifiers that are to be determined at compile time, that represent some type to be determined. And that's why we need this syntax, because we do have to declare, in this case, T, but we have to declare it in a way where the compiler knows it's not a formal type declaration. Now, this T can be anything, okay? I mean, you can label this any way you want. It can be like this. It could be lowercase. It could be all capital. We haven't yet, as a community, established enough guidelines and idioms around naming these generic types. It's something we'll have to do before this actually gets released, let's say in a year or year and a half from now. But you're going to see me with these collection types using single letters. It just feels right, these capital letters, when it comes to these collection like slices. That being said, if you look at the other examples that I won't show today, you'll see me using longer names for these type identifiers when they really specifically are for a specific input or a specific output. But these are things we got to work on. Anyway, you can see how the brackets now is the new syntax, letting the compiler know that this T has to be determined at compile time. Don't expect the developer to declare T anywhere in any source code file. But since T represents a concrete type, this is the key, that it represents a concrete type, we can write code as if that is a concrete type, as if it was an int or string or float. And we get back to code that's easier to read and comprehend. And I think that's going to be the huge win here, when generics allows us to walk away from the empty interface and walk away from type assertions and walk away from the reflect package, where using a generic type is more reasonable and practical. That's the measuring stick. and I wish there was more empirical data there, right? It's going to be somewhat subjective. But at least this first release is really going to be about where can we remove or reduce the use of the empty interface, remove or reduce the use of type assertions and the reflect package, where the code we're writing now is easier to read and comprehend by more developers in the community, on your team, so on. And I think we see that here, at least with this very first example. Now, let me run this code here just so we can see it run. And again, the tooling I'm using is a transpiler. It hasn't been implemented yet. We're just going to be transpiling this code into some Go code. If you use the build command on the command line, you'll actually get to see what that code looks like. It's really nothing you want to look at. But all we're going to do is transpile, build, and run. So the key here is I'm constructing that slice of int, and I'm passing that same slice across all 4 functions that I have. I'm constructing the slice of string and passing that same input across all 4 functions that I have. And if I change directories here, you'll see I have the go-to file there. And what I'm going to do is, on the command line, I now have a go command because of the way I've built this version of Go. And you can use a build, or I'm going to use a run command. And I'm going to pass it the go-to file. And that's going to go ahead and transpile, build, and run that code. And you can see here that the output is the same across all 4 functions, which is exactly what we should see. Now, the big thing here is this, right? Like, this is what we're trying to accomplish, right? If I come here and now want to work with a collection of floats, right? I don't have a print float function. I'd have to write that. That's not working. We know we can't use print assert because I don't have that case statement. But as we kind of talked about, these 2 functions are generic functions, right? I can pass this slice of float to print reflect because the reflect package can reflect over that data. And I can also call my generic function because we're going to be substituting that float 64 for type T. Now, if I build and run this code, we see that both of those functions were able to give me the output I wanted for this new type without having to write any more code. So it really does show that thanks to the empty interface and the reflect package, we can write generic code in Go, though I think I've hopefully have shown that that code is a little bit more complex and not letting us write traditional Go code like this using that for range loop as if we're working with that concrete type. Now, one other thing I want to stress here with our generic functions is that part of making this usable is the ability of the compiler to be able to infer the type for T based on, in this case, the call. But there may be times where the generic type is being used in the body of the function and doesn't really reflect the parameter list, let's say. And in those types of cases, you're going to have to be explicit, in this case at the call site, on what the type is. And so I think one thing I want you to kind of recognize here is that we're using the square brackets as a way, as a visual way to denote the 3 parts here: the function name, the type list, the generic type list of types that are to be determined at compile time, and then the parameter list, which is traditional for every function. The spec does say that you can use parentheses. That is still an option to experiment with, but it gets really hard, I think, when we're using parentheses everywhere. So the new use of the square brackets is helping visually. But just like this is a parameter of data input, this also represents a parameter of types, right? So what you're seeing me do is say explicitly to the compiler, oh, T here is going to be an int. Oh, float, or T is going to be a float 64. T is going to be a string. And so we have the ability to explicitly, here at the call site, tell the compiler what T is going to be at compile time. But if we want to keep the syntax more usable, then the idea is to have the compiler infer the type. And in this case, the compiler can infer what T is, because T is being used as an input parameter, and the compiler can see, well, numbers is based on an int, or float is based on a float 64, and it can do that, and that's great. And we kind of want to move in that direction to the extent that we can when we're writing code. But again, if you're using T for some reason inside the body of the function, and it's not part of a parameter list, then there's nothing that the compiler can hang its hat on in dealing with that inference. Okay, so I've shown you that. Now, one other thing I'll show you that the current draft is saying, you're not going to see me do it, but since we're using square brackets, this will also work without having to put the keyword type in there. I just ran it just so you can see it. Personally, Bill Kennedy, I like having the keyword type in there. I like it, but that's something that we have to agree on over the next year, on whether having the keyword type there or not is the best choice. So that's something you can experiment with. But you're going to see me using the keyword type, even though it makes it a little bit longer. And maybe it's just because I've been playing with this for a couple months. My eyes are now used to seeing it. At some point, like any kind of source code, it turns into the matrix, right? You're able to kind of scan it, and you know. And so that's why this is new syntax, and you may want to experiment with both options. But you're going to see me using type T. It's just how I've grown accustomed to looking at it. Okay, so I've shown you your first kind of syntax choices here now with generics. I've shown you now that we need this type list to tell the compiler that T is a type to be determined at compile time, and not a type that is going to be declared before compile time. Don't go looking for it. I showed how the compiler can infer the type, like in these cases where the input is representing type T. And I've shown you how you can also be explicit, and how this also represents a parameter list that can be of types that can be passed in like this at the call site. So I'm showing you these initial aspects of the syntax. Okay, so we've got that. Now, the next thing that I really have to show you is how to work with types that can be more generic, right? Real world software can't just be built directly on those scalar types, though at the end of the day, everything ends up becoming an integer, right? But you've got to be able to define data structures, and in some cases, it may be nice that these data structures are a little bit more generic if the operations that you're performing, like a container type, linked lists, and heaps and stacks and trees, right? Where the data itself is important, but the mechanics around how we work with that data are the same regardless of the type of data there is. So we've got to also have a way of defining types that are generic. I'm going to show you that next. So let's go through the same progression, because I know it helps me get a better understanding of what we're doing and how the generics help with the readability of the code. So on line 11, I'm defining a user-defined name type called vector int. Now, vector int is representing a vector, and the underlying type, right, the base type or underlying type for this vector is a slice of integers. And because of that, we can also add behavior now to this slice of int, to our vector int, and I do that in the form of a push method. So you can see here we're using the same value semantic mutation as append does. Push gets its own copy of the vector. It gets a value to push into that vector. We use the built-in function append to perform the operation, and the caller gets a new vector with that new value stored. It only takes us really 2 lines of code because append is doing the bulk of the work. But here we are, we've got a vector int right now and an initial API to work with it called push. And you can see on line 18, I do the same thing, except the underlying type is a slice of string. We're changing the type out again. And if you look on line 20, the push method is really identical. It's the same 2 lines of code. All we're changing is the variable names and the type information. Now, I want to make this clear. The append, the built-in function append, the built-in function copy, make, new, len, cap, all, close, delete, all of those built-in functions in Go are technically generic functions. I mean, if we really stop for a second and think about it, Go has generics. It has it in the form of the empty interface and the reflect package. But it also has it in the case of these built-in functions. Append can accept a slice of any value and a value of the same type and perform that operation. Now, let's be fair. The generic, the mechanics that are used to write these generic built-in functions, they're not extended to us, are they? We can't use them to write our own generic functions the same way that the language team is able to do this as part of the language. And so maybe it's a little unfair to say that Go already has generics like this because we don't have access to those same mechanics. But I mean, Go has them already, and I'm using it right here. The reason these 2 functions are identical is because the generic built-in function append can work with that slice of int or string and that value of int or string and do what it's going to do. But once again, if I want to work with a vector of a slice of float 64, I've got to copy and paste these 5 lines of code and do it again. So we go back through our progression. Is there a way to consolidate these vectors into one? And the answer is yes. We come back to the idea that I can use the empty interface to have a vector of any type of data because append is already a generic function. The code is identical. Look on line 20 above to line 34. And we're just changing variable names again and types. Now, let's be fair though. This vector that I'm defining on line 32 really has a different semantic than the vector that I've defined on line 18. And the semantic difference is that the vector interface isn't tied to a single type. I can interlace ints and strings and floats and users and customers and whatever. And though on the surface you might think, well, Bill, that's a beautiful vector. There's a lot of flexibility there. I'm not tied to any given data type. And look at the code, Bill, from a code complexity, we didn't really add any. The semantic is different because we've just made the usability of the vector more complex. Now, as we iterate over the vector with this empty interface, we don't know what data type we have. We've got to perform type assertions now in order to make sure that we're performing the right operations for the right data. So though the implementation in this case didn't get more complex, the usability will, and I'm going to show you that, okay? But using the new syntax, can I define a vector which has really the same properties as our vector string, a vector of a concrete type that is to be determined at compile time? And the answer is yes. And you see that here on line 46. So let's go back again to the whole idea of what we're trying to accomplish, right? What we're trying to say to the compiler is, I would like a type name vector that's based on an underlying type of a slice of some type t to be determined at compile time. Again, we're back to the idea that t isn't a declared type, but a type to be determined at compile time, right? A type of some, a piece of data of some type t. And once again, every time we want to think of that t as a generic type to be determined at compile time, we have to apply our brackets. Now, before you saw me applying the hard brackets to the function name, Now you see me applying it to the type name. So again, there's consistency in the syntax. And the funny thing is I've been writing code like this, especially in the beginning, where I start out kind of like this going, okay, I know I want some generic type T here. And then I come in and I go, okay, let me apply the syntax to keep the compiler happy that T is a generic type. Now, because of this vector being of some type T, now, anytime we're looking at that type, it's going to be this type of syntax, a vector generic of some type T, a vector generic of some type T, where T is going to be the type that we're passing in this case, right? Everything's got to be bound to the type declaration for the methods. So a vector generic of some type T, where we'll have a vector of some type T in, a vector of some type T out, a value of some type T, and again, append is already a generic function. So there we are. It's the same code I wrote before with a little new syntax to represent the idea that this T is a generic type to be determined at compile time. Okay, all good. Let's just run this program a little bit and take a look at what's happening. So you can see here I can construct a vector int set to its 0 value. We know the push methods for this vector int only work with integers. I can use my traditional for range, and I can even use a %d as a format specifier because I'm guaranteed that every value that I iterate over is an integer. No problems. Same thing with a string. I can do my 0 value construction. We know push only works with strings. We can do our traditional for range, and I can use my %s format specifier because I'm guaranteed every value is a string. Now, this is where the usability breaks down with that empty interface-based vector, because you can see here that I can interlace different values, including floating points and other things. And so now as I use my traditional for range, if I want to work with that specific format specifier, I'm back to the case statement, right? And I have to add more cases for more types. So you could see how, though the implementation wasn't more complex, the usability becomes more complex because we're back to the type assertions. Now, when it comes to our generic vectors, really the only difference is construction. And that's because you're seeing on the construction call our need to pass the type information in. There's nothing here that will allow the compiler to infer the type. When it comes to the construction of generic types, we're going to be passing in the type information here on the construction. When it came to the generic function calls, well, we had something that we could leverage to infer, but on the construction of these types, we don't. So you're going to see here that we're going to construct a vector of type int. We're going to construct a vector of type string, which now means that these push methods use integers, these push methods use strings, and I don't need case statements anymore because I'm guaranteed that the data will be of one type, and I know what that type is. We're back to the same usability that we had before, though the construction syntax now takes on the square brackets to make that explicit. And what I can do is come into O2. I can run it, and you can see the output is the same. You can even see the interlacing on the empty interface. And again, the whole idea is what? The whole idea is that I don't have to write any more code to start working with floating point numbers, right? I can do that. And if I do this right, we can change them out. I can say this is a float. That's going to be a float. I can even use the specifier. That's the whole point from the usability standpoint. And now I'm not writing any more code. I'm just now constructing a new vector that can work with that float 64. And if I did everything right, there we are. We're heading along. So there's the big win there. Now, this is a generic type that's based on an underlying type, like this collection of some type T. What about if I wanted to create a struct type that was more generic? And the other question that now comes up is, how does this all work with both our value and our pointer semantics? Because right now, everything I'm showing you is value semantic based, because when we're working with slices, that's really where we tend to be on our value semantics. So let's take a look at how this can be applied to our struct types, and then throw in some of our pointer semantics as well to get a sense of how that will work. Okay. Now, I said to you that this first release of generics that we're looking at is really focused on the reduction of the empty interface type assertions and reflection, right? To get us back to code that is more concrete based instead of API, let's say reflect based or the type assertion. So a big area here would be these types of container types. So here is a linked list implementation, okay? A very basic linked list, double linked list implementation to give you a kind of a practical view of what we're looking at here for these, for again, trying to get a win here. I'm gonna remove this syntax again here because I think it helps. Because the idea is what? I wanna define a type called node that can work or store any value of type T. Remember, we're back to this idea where the field here is going to be generic, where this node can store a value of some type T. And then the idea is that we can point to a node of that same type T. And because T is a generic type, what are we doing again? We're using our square brackets again to tell the compiler that this identifier T is a generic type to be determined at compile time. And now that represents what a node is, a node of some type T. And we know that this is a generic type. And we're using pointer semantics here because that's the linked list, works with those pointers. Now, you can see that I've defined another type called list that holds the first and last pointers to the list. And because a node is a generic type, we're going to again apply the idea that list now needs to be a generic type of some type T, which is going to flow into node all the way through there. So in order to kind of see this run, we now add a method to list. And I add this add method. Now, notice that we're using our pointer semantics on the list and the node type. The receiver accepts a pointer of type list, and the add function returns a pointer of type node. There it is. But we use the generic T here also on the add, okay? So remember, there's a type declaration of T. Here it is on the add T. And now we can accept a value of some type T to put into the node. Now, if you look on line 26, we're doing a construction call, but I'm not being explicit here with the type because this is code sitting inside the method that we have to do the construction of some type T. We can substitute the T here for the construction call. And so what we're saying here is we're going to construct a node of some type T where we store that data of some type T in the data field. The rest of that is just the pointer mechanics, right, for hooking up the linked list. But I want you to notice the construction call here. So you're seeing me define a generic struct type here where some field, one field specifically, is of a generic type. And you can see the use of the construction call here in those square brackets. Now, let me define a user type for the linked list. And I want to show you two constructions. So on line 53, what you see is me constructing a list. But again, since this is a generic type, we have to tell the compiler specifically what T represents. And in this case, T represents a user value. And because T represents a user value, the add methods now accept values of type user. And the data being stored, as you'll see, will be users, values of type user. But I can also tell the compiler, no, T is going to be a pointer of type user. which means that the add methods now accept pointers of type user, and the data will be pointers as well. So you can see here that we can construct our lists right now, either using value or pointer semantics for the data that we're going to be storing. Now, if I go ahead and we build and run this, you'll see that the func package tells us that the data are values, or because of the ampersand, the data is a pointer. Now, what if you wanted to maintain a hard rule that the data is always going to be using pointer semantics? You're not going to be applying pointer semantics here, because this syntax is to tell the compiler that the identifier T represents a generic type, right? So there's no need for the pointer semantic syntax there. T is a generic type. But what we are going to do here is say that the data that we're storing is always going to be a pointer of some type T. And we're always going to accept a pointer of some type T on the add. So we can create a hard rule that we're using pointer semantics in the storage and acceptance of the data. Now, by applying pointers there, we're going to get some compiler messages. It's a nice place to start looking at some of the compiler messages that are being worked out. And you can see here that we're having problems on the first two calls because the add method requires pointer semantics, a pointer type user. We're passing values of type user. And in this case, because we said that T is a pointer of type user, then we have double indirection for the star T, which is why this is saying, Bill, you're not passing me a pointer to a pointer of type user, right? And we're hard coding it. So to fix all of that, what now has to happen is we still pass in user as the type, but we know that we are bound to pointer semantics on the call, and it all goes back to normal. Now, I think one thing that I want you to notice is that when we explicitly state that the data is going to be using pointer semantics, or a function is going to be using pointer semantics, we kind of handcuff the usability of the type and the API. Because I think what's nice here is that, I'm going to sneeze, so I apologize. What's nice here is that the user gets to choose very clearly, do they want to work with value semantics or pointer semantics? And then the APIs follow suit. And so I think you may have situations where, no, I'm not going to leave it up to the user to determine what data semantic we use, because if I do, and they use value semantics, let's say, they're going to have bugs. So I'm going to force pointer semantics on them. But you can see how the API doesn't necessarily then match the construction call. So things to be aware of. I wanted to show you that. But I also wanted to show you how when we just work with T, that type T, it gives the user, it gives the caller or the user a little more flexibility in choosing the data semantics, like you see here. Okay, so it is half an hour past the hour. I've got at least 10 more minutes here. I'm going to probably take 15 because there's at least one more major thing that I have to, two more major things that I have to show you before we're done. So I think we'll need another 15 minutes, not 10. I'll keep an eye on that clock. And then we can go to questions and comments. And then you can use your own time to look at the rest of these examples. Now, let's get back to our generic functions for a second. The generic function that I wrote originally really had no constraint on the data because we were using the func print. We were using the func print function that's already a generic function thanks to reflection to print out values. And there was no real constraint on what the data could be of type T. But the reality is that we're going to be writing much more complex functions that are going to have constraints on what type T can be. And we need a way of telling the compiler, or at least defining what these constraints are. So let's talk about constraint right now, and specifically behavioral constraint. So you can see on line 13 and 22, I'm defining some user-defined types. They're struct types, a user and a customer. And in both cases, on line 18 and 27, I've defined a method using value semantics called string that returns a string. Now, the idea of these methods is to stringify a user or a customer. The idea is that I am creating a custom version of the user value or customer value in the form of a string. Now, you can see that I'm taking on the form of JSON. It could have been anything, but you can see how I'm stringifying what a user and a customer is. Now, I can go ahead and decide, okay, you know what? I want to write some stringify functions that work on a collection of, say, users and or customers, and then return a collection of that stringified version of each value. So here, this version of the function accepts a slice of user. On line 46, we accept a slice of customer. They both return a slice of string. And in those 5 lines of code I have, we can construct that slice based on the length of the user collection. We can use our traditional for range to do our linear traversal. We can use our generic function append. And we can, most importantly, use our string method to do the stringification of each individual user, or we use the string method to do the stringification of each individual customer. This code only works because of the string behavior that's tied to a specific user or customer. But again, I think that the majority of Go developers, regardless of how long they've been working in Go, can look at this code, read it, and comprehend it. Okay, great. Let's go through very quickly the same progression. Yes, I can use the empty interface and type assertions to consolidate those 2 functions, but we're back to the same problems. If I add another type, I need another case, right? But I get to use or write code the same way I did before, which is easier to read and comprehend. Can I make this generic? Yes, I can, but look, I just went from 5 lines of code to what? Almost 17 lines of code, something like that. Oh no, about 13 lines of code, sorry. Just went from 5 lines of code to 13 lines of code. And I think we all agree that not every Go developer, even if you've got maybe a year in, can quickly look at this code and comprehend it. It took me a little bit of time studying it. And if we look at this reflection version of the function, you can see some of the same mechanics, right? Value of, validate that it's a slice. We're changing our semantics a little bit by passing a nil slice, but we can construct the slice of string. We can iterate over using I instead of a for range. But if you notice here, I am making a call to see if there's a method named string, and if there isn't, then again, we're going to return nil. We're not going to be able to do this. These returns don't exist in our concrete implementation. But the reflect package does allow me, if I identify a string method, to call the string method. This is again why I can write a generic version of this, even when a method is being executed against each individual value, because I have the facilities to do that with the reflect package. And then I can get that string back from the call and append it. So able to write a generic function. We went from 5 lines of code to 13, using a little bit more of the API set, not intuitive, not as clean and easy to read and comprehend, but there it is. So we go back. Is there value in being able to write this using generics, where we go back to our concrete implementation, where T is a type to be determined at compile time. And I'm going to get rid of all of this again, and we're going to come back. Now, here we are again. It's the same 5 lines of code that we wrote before. So we can a lot easier for everybody to read and comprehend it. Again, we want to tell the compiler that T is a generic type to be determined at compile time. And as we've already learned today, once we define that T will be a generic type, we bring in that syntax attached to the function name, just like we use that syntax attached to the type name. So there we are. We've now told the compiler that T is a generic type. We can work with it as if it's a concrete type. Life is good. Except we have a problem. You see, this code assumes that not only is T some concrete type to be determined at compile time, but that T, any data value associated with T, has a method named string. And right now, we're not explicitly in any form telling the compiler that this is necessary. And I want you to think about this for a second. We can write functions today that accept data based on what it is. I can say, well, give me a Bill accepts values of type user. But we can also write functions today that accept data based on what it can do. And that's where the interface comes in. And if you look here on line 111, I'm basically now saying, look, anybody can call Bill with any piece of data as long as that data exhibits the full method set of behavior defined by stringer, which in this case is a string method that returns a string. Interfaces define a constraint on behavior today, and we write polymorphic functions. I'll call this our traditional polymorphic functions in Go, based on behavioral constraint. And then the compiler at compile time can validate that anywhere we're calling Bill with a piece of data, that data exhibits the full method set of behavior defined by stringer. We already define behavioral constraints in the language through the interface. And when you look at this generic function, you start to realize that we have the same situation. I have to define a behavioral constraint for T to guarantee that any value being used for type T has this method named string. And so the idea in the draft is to leverage the interface just like we do today for our traditional polymorphic functions to do it for our generic functions. And now this generic function is complete because what we're telling the compiler is that T is not just a type to be determined at compile time, but a type that also needs to be constrained to where the data for type T will exhibit the full method set of behavior defined by stringer, which in this case is a string method. And so this version of the draft wants to use interfaces to define those behavioral constraints for our generic functions, just like we're using them for our traditional polymorphic functions. Okay, great. So you can see here, I'm constructing the slice of users and customers, and I'm passing them into all four functions again. And you can come back here, and I can go into 04, and you can see it all work. Those are the stringified versions of users and customers, and you can see them working across even our generic functions. Now, I'm not going to create a new entity type. We don't have time for that. I will do is remove the constraint and show you the current message from the compiler. And I want you to see that the compiler is telling you that, Bill, we got a problem here in the declaration of the function because on line 114, you're assuming that there's a string method and that's undefined for T, right? So it's kind of really the same idea that, hey, Bill, you can't pass this data into your polymorphic function. It doesn't exhibit the behavior, right? When it comes to our traditional polymorphic functions, the compiler's kind of complaining about the data that we're passing in. When it comes to these generic functions, now the compiler's looking at the type and it's saying, Bill, you haven't explicitly said that this type does conform to this, right? This method set here of behavior. And now by applying the constraint, I'm now being precise and telling the compiler, look, please make sure that type T is a type where the behavior will exist. Okay, great. So You're seeing the use of interfaces for a behavioral constraint. I've got to show you one more thing before we finish here with syntax, and that is that there is a second type of constraint that we really don't have with our traditional polymorphic functions, but we have with generic functions. And this is an area of the spec that still needs some work. Even the language team working on this feels like there needs to be more exploration, prototyping, and work here. Okay, so as you look at this, if you're feeling like that, you're not alone. Now, I want to focus for a second on this add function on line 16. Try your best to just focus on line 16 for a second. And what I'm trying to do is write a function that can take a value of some type t and a second value of some type t, add those two values together to form a third value of some type t that we return. It's an add function. Now, in this case, to do an add operation, we need the plus operator. And I think, as we know, not all types are usable in this plus operation. You can't take two struct values and add them together. You can't take two slice values and add them together. And so we have a problem again with constraint, because we must constrain t to be of a type that can be used in a plus operation. And now we're talking about a constraint that isn't tied to a method set of behavior, but maybe more a property of the data. So how do we deal with that? Well, we go back to this at least, right? We know we need our square brackets here because t is a type to be determined at compile time. But how do we apply a constraint where we guarantee that the data or the type we use for t can be used in this expression? So the draft currently is experimenting with this idea, leveraging the interface like we are doing now to define constraints, but not as a behavioral constraint as much as a, I'm going to call it a property-based constraint. In other words, define the types that t will be constrained to by defining a type list inside the interface. And so what I've done here is I've said that t can only be of these types and these types only. Now I need you to understand that the underlying types conform to this type list. So since type bill is based on an underlying type of string, guess what? Values of type bill do implement the add-only interface in these cases, okay? So understand that though I could put bill here, because the underlying type for bill is a string, it does apply, right? This wouldn't work with our struct types, but it works kind of here. Now, this is nice. We're able to define the constraint, and we're able to guarantee a compile time that our data can be executed within the scope of line 17. But this does break interfaces for the use of our polymorphic functions. In other words, I cannot write a traditional polymorphic function like this anymore. This does not work. It doesn't really even make sense, because remember what I said to you. The idea today is you can ask for data based on what it is, or ask for data based on what it can do. And the problem is this interface isn't really based on what it can do. It's really based on what it can be. It's one of these is again, just restricting is to not just one type, but many types. And so I'm just not sure it even makes sense to write functions like bill, which only accept string. And I mean, maybe it does, but I haven't found a practical need for this. But it kind of starts to break go a little bit, because we don't have any situation today in the language where we can declare something and it can only be used in one special use case and not another. So the language team recognizes this, and this is potentially a breakdown in the current draft that we're having. Now, it doesn't mean that this ends up not being what we do in the first release, but if you have thoughts and ideas on this, the language team is very, very interested in your thoughts. So this will allow us, at least right now, today in the current draft, apply the type of constraints we need to support these operations. Now, the draft also is talking about this idea of a pre-declared type constraint. And the one that they've implemented right now is called comparable. And you can see here that maybe having a pre-declared type constraint is maybe one way out of it, where in this case, the constraint that we need to apply is on line 29. Not all types can be used with this expression. You can't compare two slices together, right? It won't work. So here's another situation where we need to be able to define a constraint like comparable, but the language says maybe we can pre-declare some of these type constraints that we know are maybe more common, so not everybody has to do that themselves. I mean, that's essentially where the built-in functions kind of came from, right? Now, I do want to show you one more thing before we're done here. And I'm going to move right over into these lines of code here. And there's a few things that I'm trying to share with you here. But I'm going to break all this down for a second. And let's start on line 75 if we can. So on line 75, I'm trying to write a function called match, which accepts a slice of some type t and a value of some type t, right? And then what happens is we do our traditional linear traversal for range, but we're saying here that match, and I'm sorry, that t, for each value in the slice of type t, there's a method named match that we want to call. So we know already that we have to define type t, and we also know that we need a constraint here, don't we? Okay, but we need a constraint on match. So above, I've defined an interface called matcher. Now, let's focus for a second just on this. Now, remember something here, that the match behavior needs to be able to accept a value of some type t. So when we go ahead to define the matcher interface, I want to say here that match accepts a value of some type t, a value of some type t to be determined at compile time that, you know, is in line with this parameter list. So where are we again? Here we've got to define matcher to not just be an interface, but a generic interface type of some type t to be determined at compile time for the match behavior. And now we have a constraint that matches line 76. Before I was showing you behavior on string where there wasn't anything generic about that method. In this case, did I just lose? It's all good. I'm almost done here anyway. So in this case, match had to be defined accepting a generic type, and you see this. Now, the other thing that I took out was this type list. And the one thing I'm trying to share with you is that we can define interfaces that have both a method set of behavior and a type list in the current draft implementation. Now, what this is doing is it's saying not only does T have to support the behavior match, but now we're also restricting T to just person and food. The reality is that this constraint is adding no value, right? It's really just about match here. And the other problem is I have not been able to find a practical example where this makes sense. And part of why the language team is asking so many people to look at their existing code bases, both personal and work, and experiment with the draft is so we might find things that we are supporting that we don't have to, like this. I mean, the only reason to support a type list is if maybe we were doing something like this, right? But we're not doing this because we have match. okay? And this really doesn't make any sense. So, not even in that form, but you understand. So I have not found a practical reason where when there is a behavioral constraint, we also have these types of operations that are not being done in the methods where we need this. I just haven't found it yet. If you find a practical constraint or a practical example where we need to constrain both behavior and type, please, 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 please send it to me because I haven't. And maybe because we come to some conclusion eventually that we don't need this, maybe that solves the interface breaking problem. Maybe we pull that out of the interface and we do it separately because we'll never have a situation where we need both. One thing you have to remember that for any type identifier in this list, if there's a constraint, there can only be one constraint. So you're not going to have a list of constraints here. Okay, it's got to be one. But if we don't have to do these types of things, we might get away with it. The only other thing I want to add here is that your list can be, this type list can be of multiple constraints. And if there is multiple constraints, comma delimited, and one of them does have a behavioral constraint or constraint like this, then they all need constraint. So you might see code in the future where you see a type list where we're defining multiple generic types, and then you see the empty interface because the other type has an actual interface on the constraint. That's the last thing that I want to share with you. But if you're looking at this code and saying, Bill, we don't really need to do this, you're absolutely right, we don't. The only real constraint we have here is on match. So there's nothing there. We don't have time, and I never have time. But number 7 is a good example for you to look at on your own. It describes two things. It shows you some zero value options that we have today when you're returning type T. And it gives you another potential practical use for generics and reducing, I think, interface pollution and methods where maybe they're not really needed. Don't have time there. But other than that, I think we've gotten a really good view of the syntax here. So I'm going to clear my screen sharing for just a second here and talk to everybody. So I see that you've been chatting, which is fantastic. I love it. I love it. I'm glad you've had a conversation as I've been going.